transmission lines. So power should be transmitted from the point of generation, from the generating stations to the substation first. Okay, so that is done by what? By the transmission lines. From the substation again to the actual point of application, right? Like in our houses, that is for domestic application or industrial commercial applications. For that we are going to use the distribution lines. Okay, so first we will deal with the transmission lines. So in order to analyze transmission lines, we need 4 parameters. Okay, so 2 of them, they are called as the series impedance. So this includes the resistance and inductance. And the second is the shunt admittance. Okay, since it is in shunt, we deal with its admittance. It is easier to deal with. Okay, so admittance is nothing but the inverse of impedance, right? So here we have capacitance and conductance. So conductance is nothing but inductance and capacitance are from different elements, right? One is from inductor, the other is from capacitor. But resistance and conductance, they are both caused due to resistive elements. But since it is the admittance part, the shunt part we are considering, we call it as the conductance. Okay. But for the actual analysis, we are going to neglect the conductance. We are only going to deal with the resistance, inductance and capacitance. Okay. So why conductance is neglected? So in order to understand why this conductance is neglected, we need to understand why it comes into the picture in the first place. Okay. So if you see the transmission lines, they will be supported at regular intervals by means of poles, right? And at these poles there is going to be insulators, because these overhead lines that we have, they are usually bare conductors and they should be insulated from these supporting towers. Okay. So for that there is insulators at each of the supports. Okay. Now what happens? Through the insulator will let a very small negligible amount of current to pass through them. Okay. So that leakage current, whatever we have, that will come out. The resistance that is associated with that leakage current is what is the conductance, right? This is the transmission line. The power, the current is being transmitted like this. Now here we have the, from the conductor towards the insulator, we have the leakage current. That means it is a shunt parameter. Okay, so that's why it's the conductance. So because that current itself is very negligible, we ignore the conductance as well. So you can write that part down. Conductance pertains to leakage current through the insulator of overhead lines. So we call these overhead transmission lines to differentiate from the underground cables. Okay. Now since this leakage current is negligible, conductance can also be neglected. Okay. So this is why we are going to neglect the conductance. We are only going to deal with resistance, inductance and capacitance. First we will deal with the resistance. So what is it? It is a series parameter. It appears as the series impedance of the transmission line. Okay. So if you remember the expression for resistance in terms of its physical dimensions of the conductor, what is it? Rho L by A. What is rho here? This is the resistivity. And what is L? It is the length of the conductor. And finally A is the area of cross section of the conductor. Okay. So this expression we know. This is the basic expression. Now this is called as the DC resistance. Okay. DC resistance. Now resistance can also be found out from the power loss. Okay. So what will be the expression then? R you can write as the power loss that is present in the circuit divided by the square of current. Okay. So this is also one way in which we can find out the resistance. There are many ways, but this is one way. Now this particular expression, this is called as the effective resistance. So why we are differentiating between these two expressions is that ideally both of these they are equal. DC resistance is equal to the AC effective resistance. So it is called effective or AC resistance. Okay. So ideally both of them they are same. Ideally DC resistance is equal to effective resistance. Now what happens practically? Practically the effective resistance is going to be more. So DC resistance is going to be less than the effective resistance. Okay, so there are many reasons for it, but two of the most prominent reasons are the skin effect and the proximity effect. Okay, so first one is the skin effect and second is the proximity effect. So we'll discuss this one by one. First we will see the skin effect. Okay. So if you take the cross section of the conductor, the current is going to be confined to the surface of the conductor. Okay. At the center of the conductor there is going to be minimal or no current that is flowing. So that means something like this. See, this is the surface of the conductor and the current density, this dotted region whatever is there, that is where the current is confined. Okay, so this is the conductor and the dotted region is the current. Okay, so you can write down skin effect is the tendency of high frequency current. High frequency means it has to be an alternating current. Okay, so skin effect is only for alternating current. We will see why. Tendency of high frequency current to flow mostly at the surface, through the surface of the conductor. Or you can say the phenomena of reduced current density as we move from surface to center of the conductor, resulting in a non-uniform current distribution across the cross section of the conductor. Okay, so this is the skin effect. Now we will see why this skin effect occurs. Once again we will consider the cross section of the conductor. Now the conductor, you can take it as a collection of annular filaments. Okay, so that means if you take one filament here, okay, so this is one filament, it is having some thickness. Okay, so this thickness we have taken. Similarly, you can have another filament near the center. This is another filament. In this manner you can consider various filaments, right? You can draw one filament here, one filament here. You can consider the conductor as a collection of annular filaments. Okay, now what we do, we will consider a magnetic flux line. Okay, so this entire thing is a conductor. We are assuming that the current is flowing through the entire cross section of the conductor. Okay, and here we have taken two filaments. Let us say this first filament, it is named A and the second filament is named as B. Now we will take a magnetic flux line. Okay, so if you take a magnetic flux line like this, if you consider the current in the conductor to be coming out of the plane, this is I. Okay, then what will be the direction of magnetic flux line? It will be, you can find it from the right hand rule, right? So it will be in the counterclockwise sense. Okay, so this is one magnetic flux line we have taken. Another magnetic flux line we will take external to the conductor. Okay, so this is the internal magnetic flux line because it is inside the conductor. Okay, internal magnetic flux line. So both are flux lines, that is important. One is internal, other is external, that's all. Both are magnetic flux lines. Okay, so now this filament A, if you take this magnetic flux line, the internal magnetic flux line is linking this filament as well as the external flux line. Okay, but if you consider the filament B, okay, it is not linking this flux line, right? The flux line is inside the filament B. Okay, so it is not linking, we don't consider that as linking. This external flux line is going to link B. Okay, now there are infinite filaments, infinite flux lines. We have taken 2 filaments and 2 flux lines to understand that the center of the conductor, the filaments that are present at the center of the conductor, they are going to have more flux linkages compared to the filaments that are present nearer or you can say away from the center. Okay, so that means at the center point, if you take, it is going to have the maximum flux linkage. If you come a little farther away, then it is the flux linkage is going to reduce a little. Still farther away, still reduction. Okay, in that way, from the center to the surface, there is going to be a reduction in the amount of flux linkage. When there is a reduction in flux linkage, what will happen to the inductance? The inductance is proportional to the flux linkage. Okay, L is equal to phi by I. We will see that later, but the inductance is proportional to the flux linkage. Okay, so when the flux linkage is reducing, what will happen to the inductance? The inductance is also reducing. Now, because of inductance, there is something called as the inductive reactance, right? What is the inductive reactance? It is the frequency into L. This is the impedance. Okay, so the impedance is also consequently it is going to reduce as we go from center to the surface. Okay, now when the impedance is going to reduce, that means at this near the center the impedance is going to be lesser. So when the impedance is lesser, what will happen? Automatically current will choose the path which has lesser resistance, lesser impedance. So it is going to be confined more towards the surface than at the center. So you can write these points down. From the diagram, we can see that the filament A has more flux linkages compared to filament, this is filament A. Okay, so filament A has more flux linkages compared to filament B. Thus, we can say that flux linkage is going to reduce, flux linkages will reduce as we go from center to the surface of the conductor. Now, what will happen to the inductance? Inductance L, as we know, is proportional to the flux linkage. Okay, so because flux linkage is going to reduce as we go from center to surface, the same effect you are going to see in terms of inductance. The inductance will reduce from center to the surface of the conductor. Okay, and the impedance, what is impedance that is associated with the inductance? Z is equal to j omega L, right? So because the impedance is directly proportional to the inductance, the impedance is also going to reduce from center to surface. So more current will appear at the surface of the conductor. So this is called as the skin effect. Okay, so this is how the skin effect will come into picture for the AC current, because the impedance offered due to the inductance, this is going to be higher for higher frequencies, and for DC has zero frequency, right? So skin effect you are going to observe in the AC currents. Now we will see what are the factors that are affecting the skin effect. The first one is what we just saw, the frequency. As it increases, the skin effect is also going to increase, okay, because the impedance is proportional to frequency, because impedance is proportional to frequency. Okay, so this is one factor. The second factor is the diameter. If the diameter is high, then skin effect is also high. And the third factor is the type of conductor. Here we will see something called as the stranded conductors. So these are nothing but smaller or thinner wires which are grouped together to form a single conductor. Okay. The stranded conductors are going to reduce the skin effect. So why is that? You can see from this picture. In a solid conductor, the current is confined to the surface. For a stranded conductor, since there are many smaller conductors, the current can now flow through the surfaces of each of these smaller conductors. So what is going to happen? The total area that is available for the current flow is going to increase in a stranded conductor. So these are the important factors that are going to affect the skin effect. Next we will see what is proximity effect. When two transmission lines are close to each other, then there is going to be non-uniform distribution. Why is that the case? First we will take the case wherein the conductors are carrying current in the opposite direction. That is, here if it is carrying current which is coming out of the plane, here the current will be flowing into the plane. So we will take as minus I. Now due to this conductor, let us name this as conductor A and this is conductor B. Now because of this conductor, what will be the direction of magnetic field lines? It will be in the counterclockwise sense, right? So you can draw the magnetic field lines like this. And here also on the other conductor also they are going to have an effect. Now since this is an alternating current, what will be the magnetic field? Magnetic field is also going to be alternating, right? So it is a time varying quantity. When a time varying magnetic field is present, what will happen to the charges that are present in the conductor B? They are going to experience force, right? So because of this magnetic field due to conductor A, there is going to be some induced currents in conductor B. Now in this region, that is the region which is nearer to both the conductors, in this region the induced currents are going to be in the same direction as this. But at the region which is farther away from the conductor, the currents are going to be in the opposite direction. Okay, so that is the reason more concentration of current will be here. Okay, so that is proximity effect. And one thing that you have to know here is the proximity effect will occur only in addition to skin effect. Okay, if there is no skin effect, then proximity effect is going to be very negligible. Okay, so this is one point, occurs in addition to skin effect. And the second point is it is more prominent for conductors which are placed closer to each other. Okay, so you can write down, this is the case where conductors carry currents in opposite direction. So the time varying magnetic field produced by one conductor will induce currents in the second conductor. This is the time varying magnetic field. Okay, and this induced current is going to make the current to be concentrated at the regions which are nearer to the adjacent conductor. Okay, so in this manner, for conductors carrying currents in the opposite directions, more current is going to be concentrated at the regions which are nearer to each other. Okay, so this is the current density. And in the second case, where conductors carry current in the same directions, the effect is going to be just opposite. The current will be concentrated on the farther ends of the conductor. Okay, so this is where the current density is concentrated.